Hello everybody and welcome to Lesson 3 Linear Programming Formulation. Previously in Lesson 2 we have discussed about models in operation research. We defined what model mean. We also discussed about the importance of models, and we also talk about the models particularly in operation research. Today in this lesson we are going to discuss about linear programming formulation. Thus, the objective of this lesson is to understand the linear programming formulation from a real problem. First of all, we have to have a real problem at hand. Then we have to formulate that real problem into linear programming formulation so as to get the optimum solution or to find out the solution for the real problem. Linear programming is a mathematical technique for the optimum allocation of scarce or limited resources. As you know, resources are limited or scarce. On the other hand, needs are unlimited or demands are unlimited. So, from these limited resources, to achieve maximum satisfaction or to get maximum utility, we have to use linear programming technique, which is used for the optimum allocation or the efficient allocation of scarce resources to achieve the maximum satisfaction. Linear programming is applicable in so many areas, like production mix, to determine the production mix, or to examine the diet problem, or to get the proportion of diet, to have media selection for the transportation problem, and etc. For the linear programming to work effectively, there are certain assumptions that should be satisfied. The assumptions of the linear programming model is, the first one is linearity. That means the impact of decision variables is linear in constraints and in the objective functions. The relationship between those decision variables in objective function and in constraints are linear. And the second is divisibility. The divisibility assumption states that non-integer or fraction values of the decision variables are also acceptable. That means the numbers or the result written in the form of A over B, where B is not equal to 0, is also accepted. And the third assumption is certainty. That means values of the parameters are known and constant. All the values are determined or known. And the last one is non-negativity, which means all the values of the decision variables are greater than or equal to 0. Or we can say negative values of the decision variables are not acceptable. Moving to the components or the structure of linear programming models, we have 4 components for the linear programming. The first is constraints. These are the limitations in achieving our objective or the resources available on our hand, which are used to achieve the objectives. And second, decision variables. These are the variables or the volume which will decide or represent the ultimate solutions for the problem. And the other is objective function. It is a mathematical representation of the objective of making a decision and represented by Z. It may be maximization or minimization. It will be maximization for the profit and minimization for the cost. And the last one is non-negativity restriction. That means all the decision variables should be greater than or equal to 0, or negative value of the decision variable are not accepted. These are the components of linear programming models. The standard form of linear programming models after formulating the real problem looks like this. Here is the standard form. The standard form consists the maximization problem or the objective function. The objective function, by the way, can be minimization or maximization, and subjected to the restrictions. As you see, here are the restrictions. The restriction or the constraints used to achieve the objective, the limited resources that we are going to use to get the objectives or to achieve the objectives. And the last one is non-negativity constraints, or all the decision variables should be greater than or equal to 0. Now let's start to formulate the linear programming model. Before that, we have to see the steps clearly. The first step in linear programming formulation is list and define the decision variables. The decision variables is represented by x1, x2, x3, and so on, xn. These are, by the way, the ultimate, represent the ultimate solution that we are going to solve. Or it represents the quantities. And the second step is to state the objective functions. It includes the decision variable in the model and its contribution to the profit or the cost. The profit or the cost. And the third step is list the constraints. The right-hand side constraints that are the limitations or the resources that we are going to achieve our objectives, represented by, from this equation, B1, B2, B3, and Bn. And the last step for formulating the linear programming model is non-negativity restrictions. Here we have to state explicitly the non-negativity restrictions of the decision variables. Let's do an example for better understanding about formulation of linear programming models from a real problem. A bakery produces only two types of burger type A and burger type B. Both burger requires flour and meat only. Each unit of burger A requires 2 units of flour and 3 units of meat, whereas burger B requires 1 unit of flour and 2 units of meat. The company kitchen has a total of 5 units of flour and 12 units of meat. On each sale, the company makes a profit of $8 per unit of A sold and $7 per unit of B sold. So this is the per unit profit of each burger. Before formulating the linear programming model from the problem, it is advisable to put the data in the table. There are two types of burger type A and burger type B, and burger type A needs 2 units of flour and 3 units of meat, and we can get from burger A sold, we can get $8 as a per unit profit, and burger B needs 1 unit of flour and 2 units of meat, and we can make a profit of 7 by selling a single unit of burger B. And we have a total of 5 units of flour and 12 units of meat on our kitchen. Thus, the first step to formulate the linear programming is we have to define the decision variables. Our decision variables are 2, that is the number of units of burger A and the number of units of burger B that we are going to make, that we are going to prepare. Let's say the number of units of burger A is x1, and let's say the number of units of burger B is x2. This is the first step in linear programming formulation. And the second step is to define or to state the objective function. Our objective function here is to maximize the profit, to maximize the profit obtained from both burgers. So the total profit is represented by Z, and the profit is the total number of units of A and B produced multiplied by its per unit profit, that is per 8 and per 7 respectively. So this is the maximization objective function. Maximize Z equals 8 times x1. 8 means the per unit profit obtained from A, and x1 is the number of A burger, plus 7. 7 is the per unit profit of B type burger, and x2 means the number of B type burgers that we are going to prepare. So this is the objective function. And the third step is to list down the constraints. The company will try to produce as many units of A and B to maximize the profit. It's obvious, as the number of A and B units increases, we can increase the profit. But the resource of flour and meat are available in limited amount. This is the constraints. Each unit of A and B requires 2 and 1 units of flour respectively. A requires 2 and B requires 1 unit of flour respectively. The total amount of flour available is 5 units. So to represent this mathematically, we can state like this: 2x1 plus x2 less than or equal to 5. We can go up to 5, but not more than 5, because we only have 5 units of flour. And for each unit of A and B requires 3 units and 2 units of meat respectively. The total amount of meat available is 12 units. So we can state mathematically 3x1 plus 2x2 less than or equal to 12. We can go up to 12, but not more than 12, because we only have 12 units of meat. And the fourth step is our decision variables that are x1 and x2 are greater than or equal to 0. Both x1 and x2 are greater than or equal to 0. So after finishing the problem formulation, we can put like this we can put as a standard form of linear programming model. That is, maximization Z equals 8x1 plus 7x2 subjected to the constraints to x1 plus x2 less than or equal to 5. 5 is the units available, the flour units available. And 3x1 plus 2x2 less than or equal to 12. And 12 is the available meat. And the other is non-negativity restrictions, that is x1 and x2 are greater than or equal to 0. This is what we call formulating the real-world problem into mathematical model. After this, the next step is to find out the feasible and the optimal solution. Let's add more problems to better understand how to formulate the real-time problem into linear programming model. The second problem is a workshop manufactures 3 types of products, A1, A2, and A3. Each product uses cutting, drilling, and polishing machine. The process time per unit of A1 on cutting is 10 hours, drilling machine is 8 hours, and polishing machine is 9 hours. And the process time per unit of A2 on cutting is 15 hours, drilling machine is 10 hours, and polishing machine is 12 hours. The process time per unit of A3 on the cutting is 10 hours, drilling 12 hours, and polishing is 15 hours. But the maximum number of hours available per week on cutting, drilling, and polishing machines are 80, 70, and 60 hours respectively. These are the resources, the limited resources that we have. Also, the profit per unit of A1, A2, and A3 are $25, $35, and $40 respectively. Thus, formulate the linear programming model of the product such that the total profit is maximized. So, we are formulating the maximization problem. Before formulating the linear programming model, it is better to put all the data in the table so as to better understand, or so as to ease the formulation. So it is presented in this table like this. So the machines, cutting machine, drilling machine, and polishing machines are listed here, and product A1 requires 10 hours from cutting machine, 8 hours from drilling machine, 9 hours from polishing machine, and we can make a profit of 25 by selling a single product of A1. And for product A2, it requires 15, 10, and 12 hours from cutting, drilling, and polishing respectively, and we can make $35 or 35 birr by selling a single item of A2. And the same is for product A3. And the hours or the limited resources are the time available for each machines. The cutting machine, drilling machine, the polishing machine. For the cutting machine, we have only 80 hours, drilling machine 70 hours, polishing machine 60 hours. So using the previous steps, we have to determine the production volume of A1, A2, and A3 so as to maximize our objective, that is profit maximization. Profit maximization, keeping the constraint. Step 1. Step 1 is we have to define the decision variable. X1, X2, and X3 be the production volumes of products A1, A2, A3 respectively. And step 2 is we have to state the objective function, that is maximization. Maximization Z equals 25 times X1. 25 means the per unit profit of A1, and X1 is the number of production volumes of A1. 35 is a plus 35 times X2. 35 is a number of 35 is a per unit profit of A2, whereas X2 is the number of product A2, and plus 40 is a profit per unit, whereas X3 is the number of A3. So this is the profit equation. After stating the objective function, the step 3 is we have to mention the constraints. The constraints for the cutting machine is 80. We only have 80 hours for cutting machine, so 10x1 plus 15x2 plus 10x3 less than or equal to 80. All the products used up a time of cutting machine not more than 80, because the maximum available time for cutting machine is 80. And the same is true for the remaining constraints. And the last is step 4, where x1, x2, and x3 are greater than or equal to 0. That is the non-negativity restrictions. After formulating the linear programming model from the real problems, we have to put in a standard form of linear programming, that is maximization Z equals 25 times x1 plus 35 times x2 plus 40 times x3, the objective function, that is maximization subjected to the constraints 10x1 plus 15x2 plus 10x3 less than or equal to 80, that is the available hours for cutting, 8x1 plus 10x2 plus 12x3 less than or equal to 70, 9x1 plus 12x2 plus 15x3 less than or equal to 60, and the last one is non-negativity restrictions. Let me add one more last example from minimization. You are on a special diet and know that your daily requirements of 4 nutrients is 60 milligrams of vitamin C, 1000 milligrams of calcium, 18 milligrams of iron, and 360 milligrams of magnesium. You have 2 supplements to choose from, Vega Vita and Happy Health. Vega Vita costs 20 cents per tablet, whereas Happy Health costs 30 cents per tablet. Vega Vita contains 20 milligrams of vitamin C, 500 milligrams of calcium, 9 milligrams of iron, and 60 milligrams of magnesium. Happy Health contains 30 milligrams of vitamin C, 250 milligrams of calcium, and 2 milligrams of iron, and 90 milligrams of magnesium. How many of each tablet should you take each day to meet your minimum requirements while spending the least amount of money? So here our objective is to minimize the cost. To minimize the cost by achieving the minimum requirements. As I said before moving to the solution, it's better to put the data in the table to ease our analysis, to ease our formulation. So the items or the nutrients are vitamin C, calcium, iron, and magnesium. And the minimum requirements are 60, 1000, 18, and 360 respectively. And this is the content of the nutrients for vega beta, and this is the content of the nutrients for happy health, and their corresponding costs are $0.2 and $0.3 for vega beta and happy health respectively. By the way, even for the minimization, the step is the same. So the first step is to define the decision variables, that is x1 and x2, the number of vega beta and happy health respectively. And step 2 is the minimization, because here is a cost. So this is the total cost. Total cost is expressed with 0.2 times, this is the cost per unit, times the number of x1, that is the number of vega beta, plus 0.3 is the cost per unit, times x2, the number of happy health tablet. So this is the total cost, that is minimization. And step 3 is the constraints. This is the requirements. The minimum requirement for vitamin C is at least 60 milligram. At most, it can be more than 60 milligram. But at least this is the minimum requirement. So we can express like 20 times x1 plus 30 times x2 greater than or equal to 60, because it is at least. At most we can go more than 60. At least 1000 milligram of calcium is required, so 500 times x1 plus 250 times x2 greater than or equal to 1000. That is the minimum requirement. And the third constraint is at least 80 milligram of iron is necessary, so 9 times x1 plus 2 times x2 greater than or equal to the minimum requirement. And the last one is at least 360 milligram of magnesium is required, so 60 x1 plus 90 x2 greater than or equal to 360. These are the constraints. After stating the constraints, the last is all the decision variables should be greater than or equal to 0. That is the non-negativity restrictions. And this is the standard form of the linear programming model, that is minimization z equals 0.2 times x1 plus 0.3 times x2, subject to the constraints 20 x1 plus 30 x2 greater than or equal to 60, 500 x1 plus 250 x2 greater than or equal to 1000, and 9 x1 plus 2 x2 greater than or equal to 18, 60 x1 plus 90 x2 greater than or equal to 360, and x1 and x2 both should be greater than or equal to 0. This is all what I have for today. Next time we will meet with another lesson. Till then, have a good time. Bye. Thank you.